Hello, everyone, and thank you for attending today's webinar, RF Enclosure Design Concepts, brought to you by Fotofab and EE World Online. Before we begin, we want to cover a housekeeping items. An on-demand version of the webcast will be available approximately one day after the webcast, and you can access that using the same audience link that was sent to you earlier. A copy of today's slide deck and additional materials are also available in the resource widget that looks like a green folder at the bottom of your screen. And also at the bottom of your audience console are multiple application widgets you can use. So if you have any questions during the webcast, this is where you ask them. Just click on the Q&A widget at the bottom and submit your question. We'll try to answer these during the webcast, but if a folder answer is needed or we run out of time, we'll make sure that's answered via email, and we capture all the questions. By the way, you can also ask questions even if you're watching this on demand. You can also expand your slide area by clicking on the Maximize icon on the top right of the slide, or by dragging the bottom right corner of the slide area. And if you have any technical difficulty, just click on that Help widget. It has that question mark icon, and it covers the most common technical issues. Okay, so let's get to know our presenter. Michael Luff is the VP of Sales and Marketing at Fotofab, LLC, a leading producer of precision photo-etched sheet metal components. He has almost 25 years of experience in business development and strategy within the technology manufacturing industry. Michael began his career in sales after graduating from Northeastern Illinois University with a history major. He grew his career in a string of sales and marketing positions, growing up the ladder as he went. At Coilcraft, Inc., he served as the general manager of the Critical Products Group and guided the specialized division to become a major market force. Now, as part of the Fotofab LLC team, Michael is responsible for overseeing all sales, marketing, and customer service functions of the business. Part of the sales team includes a team of engineers and drafters working on estimating quotes and preparing CAD files for projects. So, now that we got to know Michael, let's get to know more about RF enclosure design concepts. Michael, it's all yours.
Thank you, Amy, and my thanks to WTWH for sponsoring this talk today. So the concept of this talk came from a very frequent interaction I have with engineers where they've designed an RF shield that, they've designed a circuit board that they don't believe they're going to have RF problems with. And once they get it into the lab, they find out they need a shield very quickly. Most of the time, these people are electrical engineers, and they've never designed a metal box before. But all of a sudden, that's exactly what they have to do. So this talk is going to focus not so much on the electrical performance of RF shielding. There's plenty of information out there that talks about that. It's basically going to be, how do I make a little metal box that's going to work well as an RF shield? And there are plenty of ways to do that, so that's what we're going to talk about today. Let's get started with a little history, though. An RF shield is, like I said, basically a metal box that fits around some components on a circuit board. Or it can be incorporated into a housing of a product to provide shielding, to prevent RF leakage or leakage of RF signals from inside the device to the outside world, or to prevent crosstalk from one component or a group of components to another on a circuit board. Usually the end goal is to try and meet compliance. So Michael Faraday did a bunch of work in the mid-1800s where he suspended a cork inside a metal bucket. He electrically charged the outside of the bucket, and he noted that the cork was not attracted to the inside, but it was attracted to the charged outside. He then concluded that the bucket acts as a shield for electromagnetic energy. Basically, what works well as a shield is a box that completely encloses the components you're trying to shield against. You can have openings, but the openings in the shield must be smaller than the wavelengths you're trying to shield against, or at least oriented in such a way that leakage is trapped and cannot make it out of the shield. Board-level shielding must also be electrically grounded, which is sometimes a problem if you're trying to design a shield for a board that's already been produced. But if you have a ground plane view or something to tie into, it's certainly achievable. If you want more in-depth information, certainly more than I could possibly give you about what an RF shield actually is and how they work electrically, I urge you to check out this Wikipedia link. There's a lot of information online. Let's talk a little bit about shielding materials. Actually, even before we get there, the first thing you really have to do when you're trying to design a shield is to decide what frequencies and their associated wavelengths you're trying to shield against. Once you get that information, that will help you decide what type of material you might need in your shield application. Probably the most common materials used in shield applications are copper, brass, and aluminum in terms of mass volume of shields produced in the world. But if you're trying to shield against lower frequencies and higher wavelengths or shorter wavelengths, the magnetic materials are what you're going to have to use, and that means metal or carbon steel. Again, there's a lot of information online about shielding materials. Fotofab has this link at the bottom of the slide, but there's plenty of information online. So what are the next steps? You've already decided what frequencies and what materials you're going to use. Another decision you'll have to make is, are you going to have to get underneath the shield at any point? Or is it the type of application where you'll be able to place the shield and just leave it? A single-piece shield has a number of advantages. Well, I guess mostly one major advantage, which is cost. It certainly costs less than buying multiple pieces. But there is some ease and simplicity of construction as well. Single-piece shields can be manufactured in multiple ways. They can be etched, stamped, drawn, or a bevy of other manufacturing methods. They're pretty inexpensive and they're easy to procure. They tend to be soldered down though and not removable. But if you would need to, you can desolder them and take them off the board, but that's kind of messy. A 2 or more piece shield is designed to have a fence or other part of the shield that's soldered to the board or otherwise attached to the board, and a cover that's removable. That's held on by a number of different methods. It's obviously more expensive, but you're buying 2 pieces and you have to pay for joining in some situations. So it does increase the cost, but if you need to get under the shield, or if you have a large shield with a lot of parts that you're going to try and wave solder at the same time as you solder the shield down to the board, sometimes it's difficult to get heat under the shield. So you have trouble reflowing the components underneath. Sometimes people put cooling holes in the shield to accommodate for that. The photograph at the top on the right shows some shields with cooling holes. Another issue that people sometimes buy 2-piece shields for is that after soldering you have to clean flux off the board. And that's sort of a washing process that if you soldered a shield over your components, unless you have holes in that shield, you're not going to be able to wash the flux out from under it. So you may have corrosion problems and long life problems after you get the flux out. That's another reason people use 2-piece shields or put holes in the shields. So there's a couple of different ways that metal bends. Most people who bend metal do it in sort of a full thickness situation where you just take a piece of metal, you build the tool, and you bed the metal around the tool. If you buy photo etch parts, it is possible to put half etch bends inside your shield, whereby we etch a score line halfway through the material that provides a bend radius so that basically that part is hand bendable. It's great if you need a small quantity of shields for prototyping or you want to try out your designs. It's inexpensive, it doesn't really add cost to the parts, and there are many benefits as I've listed. The main benefits of full thickness bends though are the main benefits of full thickness bends that you don't get with half etch bends are if this part's going to be a high volume part down the road, and you're intending on buying 250,000 pieces or more, you may want your prototype parts to exactly match a production part. And if you're buying production shields in those quantities, you're going to stamp them. That's just the economics of the situation. So for that reason, you may want to go with full thickness bends for the prototypes because they're going to exactly replicate the stamp parts. However, the drawbacks are you're going to have to buy tooling to bend them. So obviously that's going to take longer, and that's going to be more expensive of an endeavor. And you may need to buy more pieces in a prototype situation as well than you actually need. So there's a design difference between the two, and I'm going to talk to you a little bit about that now. Full thickness bends, in terms of the minimum inside radius you can put on any sort of bend, is about 2 to 3 times the thickness of the material you choose. And where that comes into play is if you're trying to put a shield on a board where clearances are really tight and you have a bunch of square components you're trying to put inside the shield, you may not have the clearance to be able to put a full thickness bend on there. So you have to increase the height of the shield or the width of the shield to accommodate that for the inside radius. As you'll see in a minute, with half-edge bend lines, there's 0 inside radius. So you really can put a square component inside an RF shield with very close clearances. So I'm going to talk a little bit about the math of how metal bends, but here's a pro tip for an electrical engineer. Find a mechanical engineer who has SolidWorks or Pro-E and have them help you with the shield layout. It's pretty difficult to do it without those tools. Certainly not impossible, but the tools just make it so much easier. However, if you don't have the tools, let me explain to you how you can do it. So let's talk a little bit about full thickness bends. When you take a piece of metal and you bend it around a tool, basically you have a 90-degree shaped piece of metal that we're bending, and the material compresses to the inside of the bend and stretches to the outside of the bend. There is a plane within the thickness of the material where there's neither stretching nor compression, and that's the length of the bend allowance. That's the length of the piece of material that stays the same during the bending operation. So to calculate blank lengths or calculate the size of flat parts from finished parts is to know how much they're going to stretch or how much bend allowance we need to allow for each bend. Basically, mathematically, if you look online at all these resources, all the people who do bending tell you that the K factor, which is the distance between the inside surface of the metal and this median line, the line that doesn't change length during the bending operation, is between 0.3 and 0.5. And I think I think they're saying that just because they don't want you to know what their exact K factor is. But K factor is derived by setting up a piece of metal on a tool, bending it, and then measuring how much stretch or deformation you get in the finished blank based upon what you've calculated. So you have to try to figure out what the K factor is for each application. Fotofab has always used a 0.44 times the thickness K factor for at least the last 30 plus years that we've been involved, and it's always been a pretty accurate number. So my belief is that whether we're doing the bending or someone else is, 0.44 is a good number to use. What you want to calculate, though, is the circumference of a circle that passes through the median line in your bend. And to do that, you need the inside radius of the bend plus your K factor. So the radius you're going to use to calculate the circumference is the inside radius plus the K factor, which is 0.44 times the thickness, as I mentioned. The circumference is simply 2 times pi times the diameter of a circle. And you're basically dividing that by 4 to calculate a 90-degree bend angle, or the ratio of your actual bend angle to 360 degrees will get you the bend allowance for any bend angle. But again, this information is all available online, so please take a look. What I'm just telling you now is sort of scratching the surface. but there's a lot more in-depth information to be found. And as I mentioned before, go with the pro tip if you have that option. Let's talk a little bit about how half-etched bend lines work. Basically, the way it works is a bend channel is etched in one side of the material, usually about 50 to 75% of the thickness deep and 175% of the thickness wide. It's designed so that the math is the same for this diagram as for the previous one. We're still calculating the length of the radius for the bend allowance, but by reducing the thickness of the material that's actually being bent versus the overall thickness of the part. We're reducing the bend radius and moving the center of the bend inside the cross-section of the material. So this is a square part. In other words, if a square part were to fit inside this, it would fit exactly. So the math is the same, it's just that the radii are slightly different. Now let's talk about the different methods of constructing shields. As I said, I'll start with the simplest and work my way up. This is a single piece shield. The particular one I'm showing here is stamped or drawn can. It's the simplest, least expensive kind of can you can put on any board. But generally, tooling is going to be fairly expensive, probably somewhere in the range of $10,000 to $15,000. And the economics of that don't usually make the per piece price quantities make sense, at least not until you're looking at $250,000 to 300,000 parts a year. There are some stamping technologies that get you almost there in terms of piece part price, but you can't really go very deep on the draw. This is sort of a high volume application, so if you're in the military business, there are not many people in the U.S. that still make drawn cans. It's mostly gone to Asia for high volume electronics production. If you do need one of these, though, I would advise you to work closely with the vendor because traditional bend math does not work. It's the same way that people make soda cans. You can start with a much smaller blank of metal and slam it down into various size cavities many different times to basically stretch the metal down into the shape you want it to be. And the metal does flow sort of like liquid. There's a significant thinning of the walls and the tops. And then there are limits to the depth and size of parts and the geometry of parts you can make with this technique. Since it is sort of full thickness bend technology, you're always going to have an inside bend radius that you have to account for in terms of making sure that the part's going to fit around your components. Usually these things are available with or without a flange across the bottom. That formed flange that I've drawn there is shown in the photographs. We like to do that on our parts that we produce, mostly because it helps with flatness. This class of parts is usually purchased for a surface mount application, and we really like to ensure that those things are flat within about 2 or 3 thousandths of an inch across the bottom edge, and that flange helps us do that. It also provides a larger surface for you to more accurately place it on the solder pad in a pick-and-place operation, and it gives you a little bit more surface area to solder as well. So again, like I said, we can produce parts without that. Most manufacturers can. It just makes it a little bit more difficult for mounting or more expensive if you want to buy it with leads because you have to buy a secondary trimming operation to create the leads on the bottom after the draw. So that's drawn cans, basically, is what they're known as industry-wide. So single-piece shields are generally produced with sides that fold down from a top. They're also known as 5-sided boxes if they're not drawn can designs. The photograph at the top left is a flat shield showing the half-etched bend lines that we talked about just a little while ago. But the drawings I made are all applicable to either half-etched bend lines or full-thickness bends. It's really just the math that's a little bit different in calculating the bend allowance. The blanks really look the same except for the numbers and obviously the lack of bend lines on the parts that don't have etched bend lines. So when you're laying out a shield, one thing you have to decide upon is how do you want the corners to look? And that's really what this slide is all about. The shields at the left have what I call vacant corners, where neither side of the shield occupies any of the space that either of them could occupy, basically the space in that very corner if you extended each of those lines to the corner. They could both occupy the space, but not at the same time. So that corner method is useful when you want to run a solder bead down the seam of your shield to seal the seam. Producing a part that has vacant corners does a good job for that for a number of reasons. The main one is the edge that you just got done stamping or machining or etching or laser cutting away is usually a highly active edge. So if you're trying to solder these things fairly soon after you've cut them out and bent them, it's going to tend to want to take solder pretty nicely. And if you engineer your clearance gap in there so it's fairly small, the solder will take a nice bead down the seam and it won't occupy any additional space inside or outside the shield. It will look nice and tidy and it will be basically a good corner. If you don't want to put solder on your shield, which can obviously cost some extra money, there is another option to get things a little better sealed. That's the center drawing where you physically, you take the basic vacant corner concept and you extend one end, or basically both ends of two edges of the shield out to the extent, which means as far as you can. So it's completely occupying that corner piece of material. That basically seals up the gap for all intents and purposes. We usually work with about a 4,000th clearance gap in there, and for most RF shields, that's fairly well sealed. However, if you need a little bit more, a little bit better shielding, you can add a little bit extra flap of material to that, the end of those walls that fold over and around the shorter sidewall, or what's now the shorter sidewall. All of those things can be soldered as well if you want to do that, if you want to add the cost. The fold-over design on the right makes the shield a little more rigid. For some applications, rigidity is really important. For most shielding applications, though, thankfully it isn't. Just some additional points, though, as we go along about single-piece shields. If you're going to attach these to the board at the same time you're going to solder down the components that are underneath them, you're going to have to accommodate for heat transfer. Basically, you're going to have to put some holes in the shield to allow heat to get under it and melt the solder for the other components. Just something else to point out on this particular shield before we move on. The shield in the center has via hole leads. The two shields on the outside have no leads on the bottom and are designed for a surface mount application. The one in the photograph above is another via hole lead situation, where we have via holes that fold down from the side walls, and this is an actual shield illustrating this concept, where this shield wall is still in the vacant wall position. But this shield wall has been moved out to cover up to the edge of the shield when it forms up to a 90-degree angle. Something else to think about, this can be down to cleaning solution. If you're going to have to clean your board after you put your shield on it, you're going to have to provide holes for that as well. This can be accommodated through holes in the top, or mouse holes as we call them at the bottom. I'm going to talk about mouse holes later. That's something else you've got to think about. You've got to get circuit traces underneath those boards somehow, and I'm sure you don't want this board to short out circuits. Even if they're covered by photoresist now, they may not be long-term. Again, single-piece shields do require desoldering for rework. If that's not an issue to you, if the product you're manufacturing is low economic value and you can afford to just throw away the bad ones and you're not going to have to do any tuning because you don't have tunable components, you don't have to get under the shield for any reason. Single-piece shields are going to work great for you. If you think about it, basically assembly, heat transfer, and cleaning, they all lend themselves to single-piece shields. Just make sure you've got those bases covered and you can put the shield on after the board's been soldered, if that's an option. Then cleaning and heat transfer are not an issue for you. So I'd urge you to think about the cost. Anything you can add adds cost to the product. Try it and keep it as simple as possible. So what do shields look like in the blank format, in the flat state, before you bend them up? Vacant corners on the left is simplest. The blue region indicates either a half-inch bend line if you're going to lay these things out for half-inch bend lines, or the bend region, the bend allowance area, if you're going to go with full thickness bends. They look the same, but the math is different. So just a quick slide to show you what the three blanks look like. The main difference between the vacant corner slide and the inside corner slide is this surface has been moved to fill up the corner. Again, here on the folded over corner design, it's been moved down a little bit more, and there's another bend region added here with another associated calculation for the fold over flap. So there's your three options on corners. If you're going to go with a single piece, 5-sided fold down shield, that's what you'll get. Now let's talk about two-piece shield designs. There's a number of ways of attaching your cover to the base. They're normally set up as a base and cover, or we call them a fence and cover design. You can have through-hole tabs, you can have holes in your fence with mounting dimples, and there are a couple of other options. Many people put a T-tab that you can just give a little twist to after it's assembled. There are many ways of doing this. Just try and think as simple as possible. Here's what you can do if you need to get circuits under your board. You can put a little notch out at the bottom to run circuits through. This is a cutout in the top of a 5-sided box that lets it act as the base of a two-piece shield. And then there's another mating part that fits down over the top. This is a pick-and-place tab. Another option for the corners that I didn't discuss yet is sort of a hybrid of the two methods, where you castellate the two corners. You basically have the two pieces of metal extended so they're occupying the same piece of space. You just do it in an interluding fashion. So keeping with the theme of this presentation, try and do things as simply as possible. These two drawings are the same shield. One is made of two pieces. One is a long piece. One of the inside dividers here is made from the same materials as the outside wall. So try and think about things like that when you're designing a shield. Anything you can do to reduce the number of components is going to keep your price lower. This shield has a little step-down area as well, where there's a board designed to fit up in this cavity, which isolates it from the rest of the components. Let's move on to board mounting solutions. These two are probably the most common. Solder paste pad that your board gets soldered down to, or a via hole where a leg is engineered to fit through it. Spring clips are also a fairly common option, but they add much more cost, and really I'd recommend it only in much lower volumes. That would be very expensive as a stamped product. It's a great idea anytime you're going to get underneath your shield a lot of times though. Here's another drawing just showing the mouse hole situations and some different ideas to throw out there to give you guys for cooling holes. As far as getting liquid under the shield for cooling purposes, basically anything can be done. It's just a question of how much it's going to degrade your shielding performance and making sure that the size of the holes and the geometry of the holes is such that any wavelengths that you're trying to shield are larger than the effective openings. Earlier on in the presentation, we talked a little bit about materials used for making RF shields. Most of those materials that I mentioned are not very corrosion resistant and not super solderable without a flux. Most RF shields are electroplated for solderability and corrosion resistance purposes. There are some platings that are very commonly used in RF shielding. Okay, so just to point out as a note here before I move forward, if it's a requirement of yours, please don't forget to specify lead-free or ROHS compliant plating. Sometimes the specs can be very similar and you don't want to end up with a part that you cannot use. Anyway, to get back to the finishes, let's talk a little bit about sulfamate nickel, which has a fairly dull finish, but it's excellent for solderability and for shielding. Sulfate nickel, or nickel sulfate, otherwise known as bright nickel, is bright and shiny. It looks great, but when you try to go and bend your shield, it's very brittle. The shielding material is ductile. That particular electroplating is going to crack off when you try and bend your shield, and it's not very solderable. So there's lots of issues there, and if anyone wants advice on electroplating, please, as I've mentioned before, feel free to call us and take advantage of our engineering services. We've also put together a slide showing some online resources for everybody. Please take a look at them. They're very informative. If you have a design that you're working on or will be working on in the future, Fotofab also offers free shield design consultation. So give us a call. We can look at your design and offer our recommendations in terms of the design itself, the material selection, the plating selection, or any other aspects or questions that you may have. So just in closing, I want to thank everybody for attending today's webinar. For more information on the products and services Fotofab offers, please visit our website and download our free design guide. Thanks again.
That's great, Michael. You covered a lot of material there, some really good some basic stuff too to remind folks, and also some really in-depth information. So with that, you've inspired some questions. So let's get to the questions now. And just as a reminder, you can just go to that Q&A widget at the bottom, audience, and submit your questions. We're going to try to get to them all, but if you don't, you can still use that widget to ask questions after the end of the webinar and then while it's on demand. Okay, so Michael, the first question is, what are the relative costs of the various shield options? Because you talked about one-piece, two-piece, shields with dividers, etc.
Sure. So the way that Fotofab processes our material is on a sheet basis. So we take a piece of sheet metal, and then depending on the size of the component that you're looking for, that's how many will fit in a particular sheet. So we cost it out that way, not necessarily by total quantity of your requirement, but how many sheets we're putting through the process. So its pricing is based on that, and then it goes up from there depending on the services added to these parts. So the services could be things like forming, plating, tape and reel packaging. Tape and reel packaging is often requested when a part needs an elevated security during shipping. So there are many different variables that come up in terms of a final price.
Okay, good to know. Good checklist there. So, of course, it's always of interest to the engineers and absolutely necessary. What is the lead time for each type of shield?
Well, obviously, it depends if it's just a flat part, if we're going to form it, if there are any secondary operations, such as I mentioned before, such as plating or tape and reel packaging. Obviously, that's all going to play into the lead time. But a general rule of thumb is that a flat, non-plated part takes about 5 days. A flat and plated or formed part will take about 2 weeks, and a flat, plated, and formed part will take about 3 weeks. So a good rule of thumb is that you can add approximately a week of lead time onto each attribute that's added onto the component itself.
Okay, that makes sense. It's a little bit customized, but those are good. That's a good foundation. So you talked a little bit about the height in your presentation. So we have a question about what's the minimum height requirements. What are the minimum height requirements for a one-piece and two-piece shield?
Well, the minimum height requirement for a one-piece shield is about 90 thousandths, and the minimum height required for a two-piece shield is about 50 thousandths. The reason the two-piece shield requirement is higher than the one-piece shield is due to the dimpled and spring-fingered designs that we have for allowing the cover to sit on the fence.
Okay, that's helpful. Great. So I'm just reading the next question here, and just a reminder, audience, you can continue to ask questions, and we'll try to get to everything that we can. How many dBs of attenuation does your shield get at X frequency?
Well, we can't really give the exact calculation of the dBs, but we can typically confirm if our shield will work within a certain frequency range. So in general, shielding against frequencies of 15 megahertz or lower is a bulk material effect and can best be served by employing a ferromagnetic metal such as steel. For greater attenuation at these lower frequencies, metals with higher permeability and low core losses such as permalloy 80 or mu metal are good candidates. This will differ depending on the type of metal used. But for more specific information on your project, you can contact our sales team, and obviously we can tailor our answer to your specific requirements. Great.
Okay, it looks like we have time for maybe one more question, but don't worry, audience. We'll make sure that Michael and the folks at Fotofab get any additional questions that you may have. So finally, do you use any type of RF absorber materials there?
Actually, we have done this before, although with every new part, the situation varies. If you have a specific project you have questions on, the best action is to, again, contact us and talk through the details with our technical staff. We have a group of engineers who do exactly this. Fotofab is very big on providing our customer advice and guidance when it comes to design. So if you do have any further questions on absorbing materials or designs or metal types, please feel free to call us and ask, and we'll be more than happy to sit down with you and work on your full CAD design that you have or your napkin sketch.
Great. Sounds like a customer will get sort of a custom experience there too. So, well, that's great. Michael, thank you. We've run out of time, audience, for further questions, but once again, encourage you to continue to ask them. And also, as Michael said, you know, contact Fotofab and the technical staff, and they'll walk you through this. And obviously, they know what they're talking about. So, Michael, thanks very much. And audience, remember that this webinar will be available at www.eeworldonline.com. And check that email link that you'll get, so you can listen to this at your leisure. And, you know, tweet with hashtag EEWebinar, just for us and for you. You can also connect with us on your favorite social media channel. And, hey, don't forget about our online communities, edaboard.com and electrotechonline.com. These forums of hundreds of thousands of engineers are also there to help answer questions. There's a lot of good content there on shielding, but you know, you can check that out and obviously contact Fotofab. So, thanks very much, audience, for attending our Enclosure Design Concepts, and have a great day. Thank you.